Yes. Can I get my test?
Sure. Strong, right?
Yes.
Anybody else not get their test back? Okay. So there's a couple of sections in Chapter 3 that we have to go back and finish before we get into Chapter 4. Can you guys, let me see. Take a minute and do that problem. This has a lot to do with section 310 somehow. This needs to be like a thank God problem. Like, yes, Jeff, give me more of this. This is barely calculus, especially because this function is so easy to take the derivative of. So it really is a find the equation of the line that goes through -1, that 1, -4 that is parallel to blah. That's an algebra problem. So how do I get the slope? I need this. I got a point. Check. Now I need m. How do I get that?
Take the derivative of y. That'd be 15x to the 4th minus 7.
So now I need y prime at
1.
1. Don't plug this whole thing in for m. Oh my god. Because then it won't be linear for one thing. It's not an equation of a line then. I only need the slope at that point, not at every point. So what's y prime at 1?
15 times 1 to the 4th. It would be 8.
8. 15 minus 7. So now it's going to be, so here's what I do. Y equals 8x, I know that much, right? 8x plus something, or minus something. And x is 1, how do I make it -4? When you plug a 1 in, it's 8. Got to subtract 12 to get it to be -4, right? So I just bypass all the y minus y1 bullshit and mx plus b bullshit and just make it work. Now, nothing wrong with y minus y1. Nothing wrong with mx plus b. Not a damn thing. Do one of those two things, I love it. But you really can just tease it out for yourself pretty quickly.
Wait, can you do anything in algebra?
So I know the slope is 8.
Yeah.
Now I need something so that when I plug a 1 in, the output's -4.
Oh, okay.
When I plug a 1, I got 8 so far. Then I got to subtract 12 to make it -4. Bam! I'll solve for b. I don't do y minus y1. You know, I need it for you, Jeff. But you should be able to handle that at this level. Right? All right, anyway, doesn't matter how you got there. You got there. Now here's this. I love Desmos. We're doing this kind of graphing. Somebody, it's the one that says whiteboard. I think it's the top two, and then that one, yeah. Ooh. Well, here's the situation. Right? Where's the point that we were interested in? 1, -4. So does this do what it's supposed to do? Does this make sense? And you could do this in your graphic calculator or Desmos for your homework to make sure if the line you got was over here, that wouldn't make any damn sense. It's a nice quick check to make sure that it looks like it makes sense. This looks like it makes sense. Now, much more importantly, what section 310 does is it makes it very much in your face, something that we said kind of quickly earlier this semester. The tangent line is this function for things close to that point. When I zoom in, let me take that tangent line out of there. If I take this out, go away, tangent line. And I zoom in on the point 1, -4, does that look like a curve anymore? No. In fact, what does it look like exactly around this point? It looks like 8x minus 12. So 8x minus 12 is a great estimator for the outputs of this line, this curve, close to the point 1, -4. So for inputs close to 1. The shit, Jeff. So watch. Let me put it back in. Oh, Java. Not update. Okay. This is 8x minus 12. Now look at that stuff. Look at that. I don't know why I began bringing this up. It's an awesome estimator right here. Now, of course, it sucks really bad down here. You guys with me? The output on the green line for whatever I want is nowhere near it down here. So there's an area in which it is really close. Some of you guys might be future engineers, and you know that, hopefully you know a little bit about tolerance, right? So there's a certain max load for something, and it's got a bit of a tolerance to it. And what you want to do is you don't want to hit the max load because it could actually be a little less than that. That makes it break. So there's a bit of a tolerance, or you can measure something to be within 0.1 millimeters. That's your tolerance. So there is a range of inputs that would keep the estimation within so much of the real. So let's take this to some more concrete shits. So this is what's known as local linearity. If it's differentiable, I zoom in, it's going to look like a straight line, just like the surface of the Earth. We've talked about this a little bit before. So when I find a tangent line, I have found more than you realize. I have found a linear interpretation of that function for points near x equal 1. What the shit does that mean? I don't know. I was hoping you guys could tell me. Can you bring the lights back up for me? Whoever's back there. No? Nobody can bring the lights back up? I was like, for a minute, I'm like, are you really going to just stare me down? Do it yourself. So, watch this. What is, for the original function, somebody help me out. What do you get when you plug in 0.9? Plug in a 0.9 to that function. Oh, it's like a bit Jeff.
Negative 4.529.
So again, negative 4.
Negative 4.529.
529? Is that what you guys are getting? Yes. And look what I get when I put 0.9 into the tangent line. I get negative 4.8. It's a pretty good estimate. Is 0.9 really close to 1?
No.
We should know by now the answer to that is no, it isn't. Not really. It kind of depends on the function. This function is relatively well behaved. You guys know what I mean when I say that now? It's not like a not well-behaved function would be like in a very tight space. It changes remarkably over a very small set of inputs. This one is, okay. So it's really well-behaved. You don't have to. You should make that voice when you do it. So if I were to put 0.99 in here, these would even match better. Now if I put a 1 in there, you shouldn't have to do anything. What's going to happen when I put a 1 in there? They're both going to say what? They're both going to say negative 4. They're both built in. That is a point this goes through, and that is the point I built this guy on. So they both perfectly agree at that one point. So what this means, now watch. Let me show you one stupid little use of this. And then I'll try to, so 310, they try to make it sound like a brand new idea. But all 310 is equations of tangent lines. So when they say, find the linear approximation, that's find the equation of the tangent line. And I think I've done that enough with you, hopefully, that should be a decently easy thing to do. I'm going to try to merge the notation they use with what we do, so you can see the connection. So watch this. What about, let's do this, f of x equals square root of x. All right. So I want to find the tangent line at 4, 2. Okay. So I'm going to do this with you. So what do you get when you take the derivative? And so what is the slope of my tangent line is going to be f prime at 4. So it'd be 1/2 times 4 to the negative 1/2. I love roots for this kind of thing because if you build around 4 or 9 or something, the slope is going to be easy because it's still going to be a square root. It's just going to be on the bottom, isn't it? So what's 4 to the negative 1/2? Well, that's the square root of 4 on the bottom. So that's 1/2. So I get 1/4. How are we doing so far? That's just taking a derivative and then plugging a value in to get the slope at that point. I like it. Now, can you make the tangent line? Watch how easy this is now if you think about it my way. It's not always easy. If the point is disgusting, it's not going to be that easy to just sit there and think about it in your head. But look at this. 1/4 of 1 is 1/4 of 4 is 1. How do you make it 2? You add 1. So there's that. No x supposed to be. No y minus 1. So what does this mean? So if I want to know what the square root of 4.4 is, I can approximate it by doing 1/4 of 4.4 plus 1. Really, does everybody see that? Because what does that tangent line do? It mimics the outputs decently well, close to, in this case, 4. Whatever I build it around, it will be good approximation close. What does close mean? It depends how far off your KB. Yes? Now, just to show you what this looks like if you do the whole way out, instead of my weird little make it work way. This y minus y1. And this is a good reminder because I'm going to show you what the book's formula is. It's just this. So it'll be y minus the y piece, 2, equals m, x minus the x piece. So y minus 2 equals 1/4 x minus 1, so we get y equals 1/4 x plus 1. Eventually you get there. Nothing wrong with that. My God, I'm sorry. I don't mean to make it sound like, what's wrong with you? But you need to start loving these shortcuts, understanding why they work, and using them. You don't want to have a lot of time spent doing something that should be just a second. Okay. So help me out. What is 1/4 of 4.4? 1.1. Plus 1 is 2.1. Somebody else help me out. What is the square root of 4.4 actually? How close did my approximation get? Say again? It's 2.0 freaking 9. Right? For most humans, that's good. Right? Now, in a project where you're trying to, when you're talking about the distance between atoms, that's pathetic. So it depends on your specific thing you're working on. How okay is it to be off? How off can you be? So that's going to determine, well, how far away from 4 can I go? 4.4 is pretty far away from 4, right? You guys should be able to know, yes, it is, Jeff. Before you came to the discussion, you went, no. Now you know, shit, yes, that's a huge step. Why is this still such a good approximation? Because what does the square root look like? Draw it in the air. Yeah. That is like really, it already looks almost like a straight line there. I mean, come on. The square root function is just loving linear approximations to it. It's almost a straight line already anyway. Its slope is so gentle. Aww. Okay. Maybe. All right. So let me show you what the book has. I really dislike, I really do. I really dislike the way they make this sound like it's all new. It's its own section. It's 310. You're like, oh, it's 310. After all this weird shit, it's got to be hard. It's just tangent lines. That's all it is. So here's the main little equation we use, right? So it's a tangent to f of x at a f of a. Let me make sure you guys are all cool with that. I have a function. I don't tell you what it is. I just want to set up what it's going to look like in general for any function. So some function at the point a f of a. Okay. That's just like here. I gave you a function, and I gave you a point for f of 4. Okay. What's the m going to be? How do I find m? What do I do?
You plug in the...
Take the derivative and you plug in a in this case, right?
Yeah.
So that's the slope. So what's this equation going to look like now? Y minus the y piece equals m
F of a times
x minus the x piece.
Right.
Doesn't that look like, ooh, it's a new formula. Oh, I better memorize this.
No.
Oh, God. I hear a lot of math teachers shitting on the book, but there are little pieces of books that were like, that's stupid. And then you just add this over. Yeah. Why does this kind of make sense? Do you see how this is the y output at A? This then can be seen as an adjustment. The slope gives me an idea about how much y changes at a point x distance from A. I mean, what's on the bottom of f prime of A is x minus A. So doesn't this just become the change in y, which explains why this is the new y at some other point? I mean, it's kind of beautiful. I do like forcing students to try to look at this equation like that. But this equation is just the tangent line equation. There's no new process here. You guys semi with me? Let me show you the one kind of problem that will make it feel like there's a new process, but it really isn't. yeah. Or, sorry. I like this kind of problem because they didn't give you a function directly. You have to figure out what function to use to eventually be able to do this. So this is like that square root of 4.4 problem that I brought in at the end. It becomes the problem now, though. So obviously, what function am I using? What's f of x going to be to create a linear approximation for something like this? What's f of x? Cube root of x. I like it. And what point do I want to use to approximate this thing? Well, you can't just use like 1, x equal to 1. Why couldn't I use x equal to 1? Cube root of 1 is nice, Jeff. Because 7.9 nowhere near 1. So what's a better number to use for a cube root? 8. 7.9 is right on top of 8. You guys see how to look at this problem now? They don't give you a function. You got to figure out yourself. They basically give it to you. But then you got to figure out what number to use to build this around. Don't use 7.9. That's the problem. 7.9 is gross with the cube root. 8 is beautiful with the cube root. So now I'm talking about the point 8 what? Cube root of 8 is
2.
2. Okay. So this is really the problem. Find the tangent line to this at that point. So go ahead and do it. Let's see some old stuff here. There's Jacqueline again. Loge. Is she here? No. Remember what I said about roots? They really are cool with these kind of problems. Because the root just kind of keeps showing up. So if it's a nice number to begin with, it's going to continue to be a nice number throughout. Is everybody cool with that? X to the negative 2/3 goes down. It's the cube root of x squared. Roots are on the bottom. Just like plants. Most plants. So what's the slope going to be? Yeah, so it's 1 over 3. Cube root of 8, which we know is 2 squared, so it's 1 over 3 times 4, 1/12. And I still claim you could still do that shortcut. So it'd be y equals 1/12 x. If I put an 8 in there, that's 2/3. What do I add a 2/3 to make it become 2? 4/3. Yeah, 1 1/3 and 4/3. Or you could do the y minus y1, blah, 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 blah. And now what do I do? Well, how do I finish this problem up? Put a 7.9 in. Now, this is kind of lame. I like to do stuff where it's easily divisible without a calculator because it kind of ruins the purpose when you have to use a calculator. But oh well, use a calculator. got to find a linear approximation. So I don't want the right answer, I want the approximate answer. So 7.9 divided by 12 plus 4/3, whatever that is. Yes? Oh, 1 1/3? Yeah, it's the same thing.
Is there anyone you prefer?
Most of the time we prefer improper fractions just because it's more compact. But 1 1/3 is the same number, so I can't really complain. What the shit? I just don't want to see 1.3333. Okay, and what do you guys get? Somebody help me out?
1.9916 keeps going on after that.
I like it. And what is the cube root of 7.9? Anybody know how to do that in the calculator? There actually is a cube root button under math. And I think there's a throot button.
Math.
What do they call a throot button?
What?
See, this is... No, this is the... Why they don't?
Similar answer, but a little bit different.
Just real quick, I want to show you something. Is that you? That's you. Wow, yes. Holy macaroni. Okay, real quick. If you hit math, see that button right there? There's the third root, right? But this is what I call the throot button. So if you put in there like 3, doesn't work for 3 too well, but the 3th root. So if you wanted the 5th root, you would put 5 and then hit that button. So 5th root of, and then you put whatever you want to in there. You can also just make it that thing to the 1/5 power, yes. Because that's what a root is. So 1.9916. So, I mean, we got at least to the 4th decimal place agreement between our linear approximation and our actual function. Cool. I like it. Yay. So if you're writing a computer program and you want to, and you've got to do something like this for numbers close to 8, a billion times, you can shave off seconds from computation time by using a linear approximation instead of the actual function. Which sounds like not that much, but overall it's a lot, right? That's one little place you could use this kind of thing. If any of you are going to take Calculus 2, right? If you are, you're going to take this sucker to the next level. What this does is it makes the first derivative match. If I had extra terms for the 2nd, 3rd, 4th, it makes it fit better, fit better, fit better. Here I'm trying to take a straight line and fit it to a curve. What if my line was curved also? Wouldn't it fit better? And what if that was curved even more? That was curved, that was curved. It would fit better and better and better and better. That's something called Taylor polynomials. For some reason, students don't like them. To me, it's like, oh. You're like, yeah, we know, Jeff. Okay. Let me think. Okay. So, if you do these problems and you're worried that you're not using the same format as the book, so if you look on page 252, if you have the book, this is where they have their this. That's the one we just developed ourselves. And I think they use, they call this L of x for a linear approximation of x. So if you see those symbols, it's really kind of silly. This is just the tangent line. And we know how to get the tangent line. Okay, I like it. Blah, 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 blah. Yeah, one little thing here. This is going to help us for later. Yeah, if I have y equals f of x, I like this. What's dy dx?
df of x over x?
Yeah, in fact, let me mix notation here for a second. Right, isn't that true?
Yeah.
Now, one little thing that's kind of weird is these are separate chunks. Do you guys know, I haven't talked too much about the history of calculus, which kind of sucks. I normally do. Leibniz and Newton. You all have heard Newton, Apple dude. Right, fig thing named after, no. And then you've got Leibniz, which not a lot of people have ever heard of. Has anybody ever heard of Leibniz? And you're like, yeah, like a minute ago. Yes, you have, okay. Those two are attributed to coming up with the ideas of calculus kind of at the same time. Now, to be really honest, a lot of the ideas came out way before them, but they sort of worked with it further. So they both kind of get credit. There's all this arguments about who should get credit. We're like, just give them both credit. Shit, they didn't steal from each other. What the hell? And that's kind of like different ideas. Newton liked the idea that there were things called infinitesimals. Dx was an actual physical length. So what I could do then is I could multiply it up. Like that. See how that just multiplies up? Bam! That looks very different to us. Right? Okay, I like it. What I like about this is, now watch. What if I told you, so I have y equals f of x. And it's like a related rates problem. Related rates problem. So d by dt. Do d by dt to both sides. What would you get? So just like a related rates problem, I'm going to take the derivative with respect to t on both sides. What would I get?
dy over dt equals f prime of x.
Okay, I like it.
df of x over, no?
Inside.
Oh, dx dt.
Do you see how that's this, just divided by dt's?
Yeah.
So this is kind of like a beautiful base beginning place. And then you can put whatever you want to on the bottom to take the derivative with respect to. I love that idea. This is going to become huge when we get into antiderivatives, also known as, or eventually tied to, the idea of integrals. Eventually. Somebody loves that. I love it. I don't get that very much. Oh. Now let me write this down here. Oh, let me see. Let me use the same symbols they use. Okay. F of delta x. F of x. These two are related to each other. If I divided, so you're going to see both of these in this section. You're going to have problems that deal with both of these. There's some examples in there that deal with both of these. This is for a big step, and this is for an infinitesimally small step. In fact, that's kind of like how we developed derivatives. If I divide both sides of this by delta x, isn't that just the formula for slope? Yes, I like it. Like delta x is like h. Good old h. Okay, maybe. So this section is like reorganized old ideas, to be honest. So I kind of don't like that they make it feel like it's all new. Just realize going in, it looks new, but it's actually old ideas. When they ask you to find the linear approximation, you know that you just say to yourself, that's the tangent line. I like it. I like it. Okay. Let's see. I think the last thing for today. only 8:05, Jeff. Too bad. So the last section in chapter 3. I have no idea why people skip this section. It's remarkably important. This is going to come up in Calc 2, and then that's what I teach Calc 2, and people are like, I've never seen that before. I'm like, oh, shit. Hyperbolic trig functions. Oh my God. What are trig functions themselves fundamentally based off of? What are they based off of? What's the very first thing you work with to start to develop trig functions? The unit circle, right? They're built off of circles. We're not going to get into the whole thing about this. I'm hoping some of you guys might Google this. It's really neat. It's got a lot of neat animations and stuff that they might have showing this. But this is kind of like, what if we develop trig functions based off of hyperbolas instead of circles? What is a hyperbola, really? Yeah, it's sort of like a sideways parabola. The curvature isn't the same, but it basically looks like a sideways parabola. I don't know if you guys, do you remember how to graph a hyperbola? Didn't you make like a little, do you remember doing this stuff? And maybe this would have been an ellipse inside, but since they had a minus in the equation, it was actually maybe a hyperbola on this side, right? And if I had something like x squared over a squared minus y squared over a squared, if these were the same, but that's a minus, it would have been the hyperbola that's related to this circle. I really want you guys to see. Why would this be a true ellipse? As if that one of these was different, then it would be differently stretched in that direction. That's the only difference between a circle and an ellipse, is these two are different for an ellipse. So this is a hyperbola, but you see how it would be based on the circle of radius a. So if I made A1, then this is the unit circle, but this would be the unit hyperbola. And then I could build stuff trigonometrically off of that hyperbola. So all right. What I'm going to do is I'm going to focus on the functions themselves, but I'm hoping somebody out there Googles and finds some good animations for yourself about hyperbolic trig functions and how they really look. Right? You can do this kind of stuff with normal trig functions, right? And talk about, oh, this side gets larger as I go, and that's why sine grows as it approaches 90, blah, 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 blah. You can do similar things with a hyperbola. Okay. You can do similar things with the square, by the way. Unit square, you can build trig functions off of the square. Yeah, Google that shit. So what the shit? So basically, here's what a hyperbolic sine looks like, affectionately known as sinh. So that's hyperbolic sine. On your graphic calculators, do they have hyperbolic? Dang it! It's on the scientific calculator. They have sine h showing up. I think you have to hit math and go to weird shit. Anyway. So the sinh, this is defined to be, I always forget what order it's in. Here it is. And then the cosh is defined to be did I mention at all my cosine is an asshole theory to you guys? Cosine is an asshole, does that sound familiar? So here, cosine again, he gets the plus sign. Poor little sign gets the, all right. Sort of applies everywhere. Now, this is the definition of these two. They're built off of fantastic functions. Exponentials. Can you guys take a minute? Take the derivative of this. So I want you to realize the sinh function, this hyperbolic sine, is built off of exponentials. when you get to Calc 2, you'll see how normal sine and cosine are also built off of exponentials, but you're not going to see that here. They involve some complex numbers too. Right? If you have just a number in the numerator or denominator, it's not a quotient rule. Because that side's derivative is going to be 0. So you just pull it out like a coefficient. So now, what's the derivative of this going to be? Derivative. E to the x? Yeah. Because this would have a derivative of the inside, -1, making that plus. And of course, what is this? So just to force you in an incorrect answer, what do you think the derivative of cosh is? Some people might think negative sinh is actually sinh. If you do the derivative of cosh, you get sinh. And look at it. Wouldn't this just have a negative come down? So hyperbolic trigs do not have the exact same ideas with their derivatives, but it's really damn close. It's really kind of impressive. That is one little reason why we packaged this and called it these, because of that relationship, but also because of this, that it really is built off of hyperbolas. Okay, so they're going to talk about hyperbolic tangent. I'm not going to make you, I'm not going to force you to memorize any of this. Especially because, I don't know if you noticed, but I always forget which one of these comes first. I just do. I'm not going to force you to memorize something I didn't really take the time to memorize myself. That would be like the gym teacher's like, do 80 push-ups and he couldn't even do one. I'm like, what the shit? So I'm not going to do that. This section really is, they have derivatives of all of them, the tanh, the cosec, right? They got all that. You got inverse hyperbolic trig functions. Holy shit. So what do you have to worry about? Just do the homework directly using those formulas. I just want you to know these exist. One of the primary places you see these in action is when you put up like a telephone pole with a wire in between. You see how I did that? I mean, what shape would that wire take? You guys have all stared out the window when somebody else is driving, hopefully.
Yeah, it's like curved.
Yeah, so boom, boom. You ever done that when you're really, really bored driving somewhere? That shape, anybody know what that shape is called?
A parabola? Or like a slight parabola?
The funny thing is, its curvature is not like anything, it's like its own thing. It's called a catenary. Of course, I mean, what else would you call it? But this is defined using hyperbolic trig functions. So I think on page, where are you? Well, number 51. They have a problem with the hyperbolic cosine, and it is the shape it would take on is that catenary between two poles. I don't care how much, I don't know if you know this, but however much force you pull across on this, you'll never make this straight. That's a physics thing. You cannot make this straight by pulling straight across. You can't. It's really kind of neat. I'll let you guys ponder that. So it'll always take that slightly curved shape. Okay, so section 311, you must do the homework. I want you to know these things exist. Hyperbolic, sinh, and cosh, they come into play in Calc 2 and Calc 3 and other things, and they're really huge in engineering and all these other things. Okay, so right now I just want you to know they exist. I think I'm going to do just like a little bit of a intro into chapter 4. and then I'm going to let you guys out a little early so you can hopefully go start doing some test corrections and such. Where does this guy have horizontal tangent lines? I'll tell you there's 3 places that I tried to show you. Obviously, it's going to be at the peak and valley or trough, right? So here's a place with a horizontal tangent line. Here's a place with a horizontal tangent line. Those correspond to a max and a min for the function, right? A local max. Is this the absolute maximum? If I just say that word to you, absolute, is that the absolute maximum? Hell no. Right? Is that the absolute minimum? Hell no. But is that a local max? Oh, hell yes. Right? So it's a little hill. It's a local max. Get out of there. And this is a local min. But where else is this horizontal tangent line exist? Where else is the tangent line horizontal? Right here. Somewhere like right there. Is that a max or a min? No, it isn't. It's not a local max or a min. So what's the idea of a local max? That means within some interval around that point, all the other outputs are lower than it. Same idea with the min, except all the other points are higher than it. Here, you go out in an interval, this side the points are lower, this side the points are higher. It's not a max or a min. It just kind of was like, I'm going to turn, no I'm not. So it's like cubish over here. Is it okay if I say that word, cubish? You know, it's not elvish, it's cubish. A colleague of mine calls it the giraffe graph because it looks like a giraffe without, but I was always joking with him. I don't have a red pen, but I'm like, it lost a leg. It's just about to fall over. Or that's not nice. The giraffe. Sorry. All right. So, what can we glean from this? There seems to be a connection between horizontal tangent line and the possibility of a max or a min. So if it is a max or a min, there has to be a horizontal tangent line there. But if there's a horizontal tangent line there, is it a max or a min? Not necessarily. So we would call these 3 points, I'm going to call A, B, C. A, B, and C are called critical points. Boy, Jeff. Now there's one other situation I haven't drawn up here, but would you say that, if I add it in here, is that a local min? Don't think about anything calculus-wise. Is that a local min? Is that a local place where it gets low, the lowest? Yes, totally is. Totally. What's wrong with that in terms of calculus?
There's no horizontal line, horizontal tangent.
Yeah, there's no horizontal tangent. You can't take a derivative. The derivative is undefined here. So I'm going to add that to my idea of critical points. So critical points are where maxes and mins could happen. So when I have a problem that says find the local maxes and mins for this function, what's the first thing you do? You make a list of critical points. And then what do? You go investigate them. Right? So if you went from an infinite number of points to check to maybe 4 points to check, that's a good first step. List the places where it could happen. So find the critical points. That would be the first step. And then the next step is we've got to develop some kind of a test to see if it's a max or a min, or if it's just a little joker dude who's like, ah. So now watch. So let's try this out. In fact, let's use one of your favorite types of functions. Good. Try. Find the critical points. What are critical points? It's where the derivative is either 0 or undefined. Those are critical points. Well, this is a beautiful function. Ain't going to be no undefined in there. Some of you guys, this is your nemesis problem.